I'm very excited to have this opportunity to share my research with everyone. And the title of my talk today is The Regeneration of Porous Firn at Dai-2, Southwest Greenland from 2013 to 2019. I don't know how much background the audience have, so I will start a little bit broad. And this might be very familiar with for a lot of you. And then I will go into the details of my research. Yeah, sorry. Yeah, so we all know that Greenland ice sheet is losing mass. It is actually one of the most important cryospheric contributors to the global sea level rise. And this figure is from a 2020 Nature paper by Schaeffer and others, showing the Greenland mass balance data from 1992 to 2018. It includes data from multiple satellite estimates and also model simulations. We can clearly see that during the past 25 years, Greenland has mostly been in negative mass balance. And also the rate of ice loss has generally increased over time. For example, it rose, the ice loss rate rose from about 18 gigaton per year between 1992 to 1997 to almost 270 gigaton per year between 2007 and 2012. However, during the past several years, between 2012 and 2017, we can see that the trend has reversed a bit, and the ice loss rate has decreased a little bit. Of course, 2019 again had some extreme melt in the summer, and it is not included here. So the decreasing trend of mass loss doesn't seem to continue to now. But still, we can conclude here that the Greenland has been losing mass during the recent years, and also the mass loss rate is highly variable. And this highly variable nature of ice losses from Greenland is the consequence of different physical processes that contribute to the ice sheet mass loss. For example, the two primary ways are dynamic losses and also surface melting. Before about 2006, the majority of the ice loss happened in Greenland in the form of dynamic losses such as iceberg calving. But in recent years, however, the surface mass balance processes have gradually taken a more important role, and it could contribute to as much as half of the total mass loss. And this surface meltwater can either go to the ocean in the form of runoff, or it can also infiltrate into the underlying firn and refreeze. So about firn, we know that fresh snow is very fluffy and it contains a lot of air in the snow. But as the snow deposits and as it is buried down deeper and deeper on the ice sheet, it will become more and more compacted and finally become ice. So the firn here is an intermediate stage of the transition from surface snow to bottom ice. And it has some porosity which can let the water in. So if there is a lot of meltwater, it can form ice layers in the firn. In the ice sheet, firn is found in the accumulation zone, and it can be up to 80 meters thick. Although this 80 meters is not much compared to the kilometers thick ice sheet, it is still an important source for meltwater storage. Actually, every year about 45% of the Greenland melt refreeze in the firn. In this 2012 paper by Harper and others, they revealed that repeated infiltration had happened during the melt seasons in Greenland, and the meltwater could reach the depths of more than 10 meters into the firn. Therefore, the pore space of the firn can be used to delay the mass contribution of Greenland to the sea level rise. However, as we can imagine, the storage capacity has a limit. So in this 2016 paper, Marcus and others discussed the meltwater refreezing pattern after the extreme melt events in 2010 and 2012, showing that especially at the lower accumulation zone, these successive extreme melt events happened and created widespread thick ice layers there. And this could shorten the estimated buffering time of the firn percolation. And later in a recent paper from last year, Farring and others they mapped and predict the distribution of thick ice layers across Greenland using firn core data, radar data, and also model simulations. This is part of a figure from that paper. The blue color here indicates the distribution of thick ice layers in Greenland in 2013, which is after that extreme melt year in 2012. And these four maps are the simulation results forced by different reanalysis datasets. And these two rows are different predicted results by the end of this century. They were forced by different global climate models under different emission scenarios. For example, the RCP 4.5 in the middle row and RCP 8.5 in the bottom row. So first, we can see that the meltwater refreezing will highly likely still be a problem at the end of this century. There is no sign of disappearance. Also, there is a lot of uncertainty. For example, if we compare the figure G with figure P. So results from different models and data sets and different emission scenarios could be quite different. Therefore, it is very important for us to better and better understand this process, to know more about its temporal change and spatial variability of these ice layers, so that we can better predict its future contribution to the global sea level. So in my research, I studied the temporal and spatial variation of the ice layers in firn in Southwest Greenland. And today I will specifically talk about the site DI2. I will first focus on its spatial variability, both the coarse scale variability and also the local variability. And then I'll talk about how have these ice layers changed over time. This is a map of my study area. The inside here shows its location within the whole Greenland. And the field data was collected during 3 field campaigns in the late spring of 2017, 18, and 19. The orange dots here are all the sites. There are 14 sites in total, where we retrieved firn cores. The site DFG here, because they are located within several kilometers, so they are shown with only 1 dot here. And also these sets are located within the elevation range about 500 meter, and they roughly follow 2 lines of elevation increase. Also, many of these sites also have cores drilled by other teams from previous studies. Therefore, this enables us to compare our cores with cores from the previous research. Here are some photos showing the process, the retrieving process and the measuring process of the cores. So the cores were usually drilled to the depths of from 5 meter to 20 meter, depending on the core structure and also the local topography. Also the cores during the retrieving process, they were usually naturally broken into segments or pieces, or if it's too long, we will cut them into shorter pieces. And then the detailed measurements for each segment were done in the field. This includes like length, weight, diameter, intactness of the core segments, and also the location and thickness of ice layers in the firn. And then densities were calculated for each segment based on this data. And if there's any data gap or unrealistic values or errors, they will be either filled or corrected. These are some example photos of the cores. For example, in the left figure, the left photo, we can see most part of the segment is firn, but still there are some ice layers. Out of these 14 sites, here is site Die2, which I will talk more about it later. Okay, so this is the refreezing and snow accumulation data at Die2 during the past 30 years, simulated using MAR version 3.10. And the red line here indicates the change of snow accumulation, and the blue line is refreezing. So one thing to notice here is that the year is not the calendar year, but rather firn core year, which starts on the May the 1st of the previous year and ends on April the 30th. So for example, the 2013 here refers to the from May the 1st in 2012 to April the 30th in 2013. So for example, recently there were several really high melt years where there were a lot of melting, therefore a lot of refreezing. They are 2010, 2012, and 2016. So in this figure, they are shown as 2011, 2013, and 2017. And during the past 30 years, while the red line, the snow accumulation fluctuated around a roughly similar level, the refreezing has a generally increasing trend, especially since the early 2000s. But in the recent few years, it also shows a slightly decreasing tendency. Although it is not very accurate to fit a trend line here because there's so much noise, I still did one just to show the general trend. So first, this is a trend line for the refreezing data in the past 30 years. We can see it has been slightly increasing. I also did one only for the past 6 years from 2013 to 2019. Although it also fluctuated a lot, it is slightly decreasing. Of course, the summer of 2019, which is after this data, had a lot of melting. So we can say that the melting is decreasing. But it is clear that while the snow accumulation doesn't change much, the refreezing is more variable. And it is in a generally increasing trend, but also decreased a little bit during the past few years after 2012. And this also agrees with the total mass loss trend of the whole Greenland. Well, previous studies talked a lot about the thick ice layers formed near surface after 2010 and 2012. There is less discussion on what happened after that. Particularly, the last few years didn't have that much melt. So there are some questions, for example, are those thick ice layers still there filling the near surface firn? Or is it possible that they have been migrating downwards into deeper location? And also with this kind of several normal or low melt years, could the firn regenerate near the surface? Yeah, so before diving into Die2, let's first take a quick look at the whole study area. So this is a stratigraphy figure of the site G core here. Its location is shown in the map with the red dot. So the y-axis is the depth from surface. So here the top is the surface and the bottom is 30 meters below surface. Also, this core is only 10 meters long. So below 10 meters, the white part is just blank. The x-axis is density, and the black line here shows the density variation with steps. So the blue color indicates the presence of ice layers, and the white color at the top and between the blue parts is either snow or firn. And this IG core is almost filled up with ice layers, and we can see that the densities of those ice layers are almost close to pure ice density. Okay, now here are the 14 cores from the 14 sites. Some sites have multiple cores, but I only included the longest core at each site. And they are listed in the order of elevation. So from a low elevation at left and high elevation at right, from about 1900 meter above sea level to about 2355 meter. Yeah, so these cores were not drilled in the same year, but within 3 years from 2017 to 2019. This is a relatively short time period, and also because I'm not doing any detailed analysis here, so I will ignore the time difference here and just look at the spatial pattern. In general, the density is always smallest in the top snow layer and increases gradually as we go deep. Also, we can see that all these high values correspond quite well with the presence of ice layers. And the densification here is caused not only by the compaction of snow as we go down, but also the presence of this ice. Also, through visual inspection, we can already see that the ice content of the cores has a very obvious trend. That is, as the elevation increases, there is less and less ice, and the ice content decreases. To quantify this change with elevation, I took the top 10 meters of all these cores, which is the largest common length of this cores, and calculated the average density and also ice content of each core. Here, the left figure is the average densities change with elevation. Each blue dot represents one site, one core. And the red figure is the ice content. Both of them show strong elevation dependence. And this is mainly due to the elevation dependence of melting and refreezing. So I showed the MAR simulated data at DI2 before. I didn't include the MAR data for other sites because this is not the focus of not today's focus. But to simply summarize, so our 14 sites are within an area with elevation range of about 500 meters. But in this area, the modeled snow accumulation is actually quite similar across all the sites. But at the same time, the refreezing has a strong elevation gradient. So the higher the elevation, the less the melt, the less the refreezing, and also the lower the density and the less the ice. So this is the core scale spatial variability of ice layers in our study area. And out of this 14 sites, DI2 is located at about the middle place, both in terms of elevation and in terms of the ice content. And yeah, here the red dot shows the location of DI2 in the map. And this is actually a quite interesting site. It is very different from those higher elevation sites, for example, EKT, because EKT, you can see that it has relatively less ice compared to the other cores, and most of the ice layers are very thin ice lenses. And in addition, compared to the bottom part, the top part of EKT has a little bit more ice content, but not much more. And also, this site has not been strongly impacted by those extreme melt events, because even in those high melt years, there was not much melt there. Yeah, and also Daichu is quite different from the sites at the lower elevation. For example, site G is almost filled up with ice, and in that core, only the top 2 to 3 meters are not that icy, and that part is just from the last 2 to 3 years. So those successive high melt events from 2010, 2012, they created a lot of refrozen ice, which filled the near surface of the firn there. And this strongly affected the percolation of meltwater at that place. In Daichu, there are signs of some big ice layers from previous extreme melt events, but there are also some signs of possibilities of regeneration of porous firn at the top. So yeah, therefore it's a very interesting site, and also we have the most cores there. So therefore that's our topic today. Now let's have a look at Daichu. This figure includes the 15 cores retrieved by multiple teams at Daichu from 1998 to 2019, covering more than 20 years. And the leftmost core is 1998 core from the Parker project. Then there are cores from 2013, 15, 16, and 17 drilled by the Mahagus and McFerrin teams. And then the right 7 cores are our cores from 2017 to 2019. With a quick look, we can see that the ice content in the 1998 core is apparently very different and a lot less compared to all the other cores. And for the other 14 cores, the ice content across the years seems to be decreasing a little bit, but it's really hard to tell with just looking at it. Besides, we can also see that some thick ice layers seem to be moving down from year to year. And we'll discuss about all this in details in the next few slides. Yeah. So before we go to the results of the temporal change analysis, it is important to talk a little bit about the age depth relationship at the Daichu site. Because in a core, the different depths correspond to different ages or years. Therefore, the depth interval we pick for the analysis could affect the results a lot. In particular, this region has experienced quite dynamic weather recently, so different depth intervals may give us very different conclusions. We didn't have direct age depth data at the Daichu site from our fieldwork, but we did date one core at the site core 8 in 2018, which is a site about 100 meters higher than Daichu. Also, there are 2 legacy cores at Daichu with age depth data, and there is 1 core from a nearby site, site J, which is quite close to Daichu. These 4 age depth relationships and their average are shown here using different colors. This data suggests that the top 5 meters were deposited approximately in the last 6 to 9 years before the core retrieval. And then the top 10 meters were from about the last 13 to 15 years. And the top 15 meters were from about 20 to 23 years. And these age estimates are just approximate because of the uncertainties associated with the determination methods, and also because the age depth relationship changes slightly over the year. but still it can provide us with a reference of the age depth relationship I die to. So for this course, because besides this several 5-meter short course, most of the course are at least 50-meter long. Therefore, I split them into 3 segments for further analysis. They are from surface to 5-meter depths, 5 to 10 meter, and then 10 to 15 meter. Yeah, so here the top row is the temporal change of average density for the 3 depth intervals of all the cores, and the bottom row is the temporal change of ice content. The red lines are the trend lines fitted to the 2013 to 2019 data, and the 1998 core it's clearly an outlier here. It has a lot lower density and ice content compared at all 3 depth intervals, and therefore it is not included when fitting the trend line. The 3 depth intervals have very different trends, and for each depth interval, the density and the ice content have quite similar tendency. And now let's examine them one by one. So first, here are the top 5 meters, the density figure, ice content, and also profiles of the top 5 meter of all the cores. The surface to 5-meter depths roughly correspond to the last 6 to 9 years before retrieval. So for example, here in this 2019 core, the thick ice layer at the bottom at 5-meter depths is likely from 2010 to 2013. And yeah, I also mark this time range of this core in the MAR data here. Yeah, and then for example, the 2013 core, the bottom thick ice layer is likely from about 2004 to 2007. So in this top 5 meter, both the average density and the ice content show a generally decreasing trend with some fluctuations in the past 6 years. The 2017 cores, for example, have high average density and ice content compared with the 2016 core, which can be explained by the high melt event in the summer of 2016. Also, while the 2013 cores have quite similar numbers, the multiple cores from 2017 and 2018 presents higher variability. And we can also actually see this decreasing trend in the stratigraphy figure. During these years, we can see that the thick ice layers from previous melt events are gradually moving down. And also in the top, we can see only thin ice lenses have been created. Therefore, both the average density and the ice content of the top 5 meter are decreasing. Then this is the depths from 5 meter to 10 meters. The cores grayed out here are the ones less than 10 meter long, so they are not plotted. Therefore, the figures here only contain 9 data points. The density and ice content in this depth interval, those show increasing trend, which is opposite to the trend in the top 5 meters. As mentioned before, the top 10 meters were deposited about 13 to 15 years ago. So for example, the 2019 core covers approximately from 2005 to 2012. And the increasing trend is also quite clear in this profile figure. For example, as mentioned before, the refreezing I die to has increased, especially since about 2005. and until 2012, which is actually the time interval contained in this 2019 core. And as for those earlier cores, for example, 2013, its top 5 to 10 meter depths were deposited approximately during the late 1990s to the early 2000s, which is actually before the increased peak of the refreezing. Yeah, this shows the moving down of the thick ice layers. Finally, these are the depths of from 10 meter to 15 meter depths. Also, the 6 short cores were grayed out here and not included in the plot. The 10 to 15 meter depths were deposited about 20 to 23 years ago before core retrieval. So, for example, the 2019 core covers approximately from 1997 to 2005. And the trend lines of, yeah, and here's 2013. So here the trend line of average density and ice content are again decreasing. But the lines don't fill to the data points as well as before. Yeah, as we can see. So there are more outliers and noise. So as shown in this MAR figure, the refreezing during this time period fluctuated a lot, and it doesn't have a very clear increasing trend. So this probably is the reason of this slightly decreasing trend at this depth interval. Finally, let's talk a little bit about the local spatial variability at I2. So as mentioned before, we have multiple cores at from 2017 and 2018, and they show quite some variability in their density and ice content values. So because out of these 9 cores, 6 cores are just short cores of about 5 meters. So here I only included the top 5 meter for this comparison. All the 5 cores from 2018 were drilled by our team, and these cores are 10 meters apart from each other, so they are very close together. The left 3 2017 cores were drilled by another team. Yeah, they're also close to each other. And the right 2017 core was drilled by our team. So for the 2017 cores, although they are at the same site, but they may have some distance between. And also the drilling and measurements were carried out by 2 different teams. So this could also cause some uncertainty. As shown in these figures, though these cores are within a near distance, like tens of meters with each other, their statistics are not very similar, which indicates a lot local variability. For example, in these core profiles, we can see that, for example, for this core, the depths and thickness of most of the ice layers appear to be very uncorrelated with the ice lenses from another core from the same set from the same year. The only exception is the pronounced ice layers here. They have quite similar widths and depths in different cores and are actually traceable across the cores from same year and also from year to year. Lastly, I also compared the statistics of these 9 Die2 cores with the cores from all the other 13 sites. So here the red circles shows the Die2 cores. Yeah, and the x-axis is elevation, which also corresponds to the different sites. We can see that although there is some variability, the data points are still distinguishable from like the numbers of some faraway sites, such as site G. However, the local variability of DAI2 also makes its data range overlap with the data range of sites within a near distance, like about 100 meter, and it can even overlap with as much as 250 meter elevation difference.
Can I interrupt you 1 second? There's a question from the chat from Allegra.
Yeah, sure.
Allegra, would you? Yeah, thank you.
Sure. I was just wondering. So you seem to make the point that the big layers, there is some coherence for the big layers, no matter where the core site is that you're drilling. But that to the key question about like SMB, is the storage capacity for water in the firn being impacted by having those layers, or are they actually, is it, if you did enough cores, would you find them missing? And so it's not, you know, that there's still ways for surface melt to get through and into deeper layers.
Yeah. So this is a great question. So first, as for the storage capacity, I mean, yeah, from this field data, field course, it is really hard to quantify their impacts on the unblocking the meltwater. What we can get here is the ice layers change spatially and also across a year. And as for if it's really impeded the percolation of meltwater, this is still a question that hasn't been answered. But as for me, I think it really depends on different sites. For example, in our course, the DAI2 one I pick here, I think it's the most interesting one because it's both shown the thick ice layers from those extreme melt events. So that means those extreme melt events happened here, and it created some thick ice layers and perhaps affected the percolation for the next coming several years. But with several low melt years, or normal melt years, which are 2013 to 2019 here, there is actually a sign of regeneration of firn, so which is actually very interesting. But as for for like set J, which is at the lowest elevation of in my study area, there are the thickest ice layers there, and even during the past few years, I don't see any a lot firn there, so they are still like filled up very seriously. Yeah. And also then at the higher elevation, like the EKT site, even those extreme melt years in like 2012, it didn't really cause a lot of ice there. There are only just thin ice layers. Yeah. So as for among these three types of sites, which I summarized, I think the DAI2 site is the one like showed actually presents us the different influences of different melt years, melt periods. Yeah.
Thanks.
Yeah. Yeah. So yeah, actually, my presentation has come to the end. So finally, here are some take-home points from my talk today. So first, we talked about spatial variability. As for the coarse spatial scale spatial variability, in our study area, the ice layers take up a considerable portion of the near surface firn cores here, and the ice content has, and also the average density has a strong elevation dependence. It is higher at lower elevation where more melting happened, more refreezing happened, and more ice has been created. Second, about the local spatial variability. So within a slight elevation change, for example, 100 meter in our study, we find that the local variability can be quite large and even surpass the elevation ice content trend. But at the same time, a single core can still provide us with the with quite reliable data of the box statistics and of that site. Also, the dominant ice layers seems to be more evenly distributed at a site. Then about the temporal variability. So the temporal changes of ice content at Die2 vary with different depths, and this can be explained by the interannual variability in the melting and refreezing. Yeah, finally, about the regeneration of the firn. So prior research shows that an extreme melt season can result in a sudden increase of refrozen ice in firn. But we show that several years without extreme melt can actually regenerate some porous firn near the surface and also cause the downward advection of thick ice layers. Yeah. Last, I want to acknowledge my wonderful collaborators. Yeah, thank you.
Thank you very much. That was a really interesting talk. There are a couple of questions in the chat, so I'm going to back. There was one from Vivian that perhaps I should have gotten to earlier.
Yeah.
She asked, is the elevation ice refreezing relationship related to temperature, i.e. where the lower elevations are warmer on average than the higher elevation?
Yeah. As for the case in our study area, it's pretty much because like the snow accumulation is similar, so the only thing that changed a lot is the refreezing. Yeah, and it's related to the temperature.
We have another question just a moment ago from Klaus. Klaus, would you?
Well, I mean, it's related to what Vivian asked. I wondered whether you had temperature and maybe even wind data in your site as a function of elevation. It would be nice so one could get more at the causal relationships between temperature and refreezing.
Yeah, this is a great question. So, cause my focus was more on still on the patterns of the ice layers, so I didn't do much work. I just analyzed the relationship between the ice layers and refreezing, and I haven't done much about the temperature or like other precipitation and wind with the refreezing. Yeah, so that's definitely something to do in the future.
Thank you.
Do we have any other questions?
Maybe you already said, but is this the site? Is it homogeneous? Like when you look at it, is it all like a dome and all equally flat, or is it more variable than that?
Yeah. Let me get back to the map here. Yeah, so there is some local topography, but it's definitely quite flat. Yeah. So for example, like there are some local feature, for example, like the catchment C, the SETI FG here is not only just at lower elevation, but also the topography there is actually kind of low point compared to the others as a catchment. Yeah, so this definitely is one of the reasons why there are so many ice there. Yeah.
So like for modeling surface mass balance, the surface roughness length term is often super important.
Mm.
So how do you think we could make that better? Or do you see things on the ground that we could be using to better parameterize that?
You mean the roughness, the surface roughness parameter?
Yes.
Yeah, yeah. Actually, currently I don't have an answer for that, because I think the surface roughness, like so first is because there are like so many winds and precipitation there. So I suppose is if we want to go into so details, it will just change always. Yeah. And then if we zoom out a little bit, look at the a little bit coarser scale surface topography, then we would miss the local variability here. Yeah.
Okay, we have another question in the chat from Vivian. Vivian, is there any chance you'd like to unmute for the question?
Yes, I'm just wondering what the broader implications are of this work. I mean, it seems to imply that since the lower elevations show more of these ice layers, and usually those would be at higher temperatures, that as temperatures rise in general, and particularly near the ablation zone, does that mean that the formation of these ice layers will act as a negative feedback on runoff and you know, contribution to sea level?
Yes, of course. So so the pore spaces in the firn is initially actually a buffer against the melt salts, because it will store the meltwater. I mean, as much as 45% for now, but as with those more and more high melt events, high melt years, more and more water went into the firn and refroze there, and therefore actually close the pore space there. Therefore, it will, in the future, I imagine, act as a more contributor to the more add to the sea level.
We have a question from Klaus and then David Holland.
Well, I mean, following up on earlier thoughts, do you think, given the insights you gained now, that in the future one could develop a whole, what I call hydrological model, meaning including topography, temperature, precipitation, and the porosity with densification and everything, to really model the whole process? Is that conceivable?
Yeah. So currently there are actually some firm process models, but they are all have different advantages and they are all not perfect. The biggest difficulty here is that there are a lot of complicated processes in the firm. Just for example, like one difficulty is always about like how should we decide the percolates of water. Like for example, some firm process model will just suppose the water will always infiltrate the firm column, even there are ice layers. Some will set some threshold of blocking, but these are also not sure. Like for example, some will decide a certain thickness. Some, So there are some there are many different processes that we are not sure about, and I don't think we'll be sure about in near future. Yeah.
Well, in particular, if it's a truly three-dimensional problem where these layers, ice layers, may be more lenses rather than layers, right?
And also in addition to this vertical process, there are also in reality, there are also some lateral processes will also affect our simulation. Yeah, and also this will relate to the local topography.
Thank you. There's a question from David. David, would you like to unmute?
Hi, Jing.
Hi.
Hi. The offshore from Die 2 along the west coast of Greenland, we can see in the last 3 decades variation in subsurface temperature. 1997, a warming, 2010, a cooling, 2011, warming, 2016 to 18, cooling, 19 to now, warming. So a bunch of numbers and a bunch of up and down. Does the firn see any similar variation that's in synchronization with the ocean? You know, or vice versa?
Yeah. Yeah, like based on this years you provided here, there's definitely some relationship, but I don't think it's like synchronous one. Yeah, there seems to be some time gap. For example, as for the the temperature in this study area, the several really high melt years in the past decade are 2010, 2012, 2016, and also 2019.
Okay, interesting. The ocean seems to be driven by the North Atlantic winds. So there might be a small relation there, but something to look at maybe in the future.
Yeah.
Thank you.
Thank you.
Thank you very much. Are there any further questions, perhaps final questions? Give it a moment, someone might be scrambling for an unmute. Silence. Okay, I think we're coming up close to our end time now, so I should probably just say thank you very much again, Jing Xiao, for a fascinating talk. Great job, says Sasha. Great. Thanks everyone for joining us. Thanks again for your talk, and I hope everyone has a great rest of the day.
Yeah, thank you everyone.
Thank you. Bye.